In this video, I want to explore how the normal distribution can help us solve some binomial scenarios that mathematically might be a little bit challenging. Let's begin though with an easier example. Let's say that you've got a die and you're going to roll it 31 times. And let's say that you want to calculate the probability of getting a 4 at least 3 times. So we want to get this at least 3 times. Well, we could do the probability for 3 times, and 4 times, and 5, and 6, and so on up to 31. That would be a lot of work. Instead, perhaps solving this indirectly would be a better option. Take all the probability, the total, 1, and subtract out when we don't get any 4s, when we don't get any, when we don't get 4s, when we get 1 4, and we get 2 4s. So, let's begin by filling out our variables for a binomial distribution. Number of trials, probability of success, 1/6. Probability of not getting a 4, 5/6. And let's let x be anywhere from 0 to 2. So our probability of getting a 4 3 or more times is 1 minus our probability of getting no 4s minus getting only 1 4 out of all 31 of those trials, and of getting only 2 4s out of all those trials. So the probability for a binomial distribution is equal to the number of trials, 31, choose x. So let's let x be 0 first. And then we would have our probability of success, but there are none of them in this particular scenario. And then it means, of course, that all 31 of our rolls were unsuccessful in getting a 4. Let's do this again, but this time let's take all 31 and let's get a 4. So we have 1 success, but we're going to have 30 failures, if you will, or not getting 4s. And then finally, let's do 31 trials. 2 of them end up being 4s. Means we get 2 successes and 29 failed rolls, if you will, or rolls that are not 4s. All right, we can punch all of this in. I'll help you with it. Comes out to 0.909, which when you round it comes out to approximately a 91% chance. So there's a 91% chance that you can get a 4 at least 3 times when you roll the die 31 times. And that makes sense. That's reasonable. Okay. What if we change the scenario a wee little bit? What if we said instead, hey, instead of getting anywhere from none to 31 4s, what if you wanted to find the probability of getting 16 or more? Well, then you'd have to find the probability for 16, 17, 18, all the way up to 31 and add them up. That'd be a lot of math. And similarly, so this would be direct. To do it indirectly, we would have to take 1 minus all the scenarios or probabilities we don't want, which are these guys, which again, that's a lot of math. So what if the probability could be found a different way using the normal distribution? We've been learning in this unit how easy that is. Let's go back to just 3 trials to show how the normal distribution could be used. Now, when we apply the normal approximation to a binomial distribution, there are 3 criteria that need to be met. The first one is that the mean, n times p and n times q have to be bigger than 5. So there's 2 of the criteria. The third one is that we're trying to apply something continuous to something discrete. We're going to have to use a continuity correction in there too. Let's walk through this process. First of all, let's know that when we apply the normal approximation binomial, it works best when we have lots of trials and when p is really, really close to 0.5. Those are sort of optimal conditions. Okay, the approximation works at its best. Now, of course, to use the normal approximation, we need a mean and a standard deviation. Well, the mean can be thought of as being the same thing as the expected value in a binomial distribution, which means we can find the mean really easy doing n times p. So let's do it then using our values up here. Let's do 31 trials, probability of success 1/6. We get 5.17. And in calculating our mean, we can also do is this value greater than 5, so that we can apply the distribution. We've met that criteria number 1. That's good. While we're here, let's see if NQ is going to be greater than 5. Well, N is 31, and our Q value is actually bigger than it was for successes. It's gone up from 5/6 to 1/6. So I don't even really have to do the math. I know that when this was 1/6 it already met, so that criteria is going to be met too. I don't actually need the value. I just need to show that it's greater than 5. All right. So now we want to, again, find the probability of being able to roll a 4 at least 3 times, so 3 times and more. But again, this is a discrete value, so I have to do my continuity correction here as well. So again, sort of thinking of this as a distribution, we know that the mean's at 5.17, and here we are at 3. If we want to find the area of the curve that is greater than 3, and we want to include that number 3 in that area, we can't start after the 3 because it won't be included. We're going to have to start before the 3, which means we're going to have to start a half unit less, which means that we're going to have x being greater than 2.5. Now, when we punch this into Google Sheets, and if you don't have it open, pause the video and go ahead because I want you to be able to follow along and try it as you go. We know that when we're finding the area of a curve that is from a point greater, we need to subtract 1 or have 1 minus the smaller piece or the piece to the left to get the piece on the right. So in Google Sheets equals 1 minus norm dist, and we'll put in our x value of 2.5. We'll put in our mean, which is 5.17, and it's nice to carry a couple extra digits just for getting the best answer we can. Our standard deviation we did not figure out yet, so let's pause here for a second and do that. I forgot to mention it. I will give you the equation for standard deviation. It is standard deviation is equal to the square root of NPQ. I like saying it that way. It's also alphabetical, so it's easy to remember. So our N value is 31. Our P is 1/6, and our Q is 5/6. And when you go ahead and punch all that in, do all the multiplication and square root of the answer, you end up with a standard deviation of 20.7. So I'm going to put that in here right now. And then we're going to end, of course, with the word true when we're in Google Sheets. So this is what you want to enter into any cell of Google Sheets, including that equals, so it knows it needs to do a calculation. When you hit enter, you should find that you get 0.901, which when rounded comes up to 90%. And that is awfully close to what we got using binomial methods before. Now we're able to make this comparison because it was 3 times or more, but if it was 16, I think I'd rather do this method than this method. Let's look at another example. This time, let's flip a coin, but let's flip a rigged coin. A coin that does not have a 50-50 chance because one side of the coin is made of a heavier metal than the other, even if it might be covered up, say, with copper or with silver or something on the outside. So we've got a weighted coin, and the chances of getting heads, or the probability is 0.3. Probably getting tails is 0.7. Okay, so that would actually mean that there's a better chance of getting the heads up. If it's higher, it means the heavy side must be on the head side, because otherwise it'd be hard for the heavy side to get on top. That's why it's got a lower probability. So what is the probability of getting 10 or fewer heads if you flip this coin 60 times, and what's the probability of getting exactly 20 heads if you flip this coin 60 times. Regardless of which of those questions we answer, we have some prep work to do. So because it's binomial, we need to look at what is our n, what is our p, and what is our q. So number of trials is 60. Probability of getting ahead is 0.3, and our probability of getting a tail then is 0.7. And of course, we're interested in getting heads, so we're going to define heads as the probability of success, or the thing that we want. In our first example, we are going to have 10 or fewer heads, so it means the value of 10 is included. We need to find the mean, which is n times p. It's the expected value for binomial. And we can also see if it's greater than 5 here too. So 60 times 0.3 gives me a value of 18. It is greater than 5, so we're good to continue on to the next step. Next step is, what is n times q? Well, 60 times 0.7, again, you can appreciate this is going to be even larger than n times p was. It does come out to 42 just for fun, and again, your greater than 5 criteria has been met. So let's go ahead and find the standard deviation then too. It's the square root of npq. So we have the square root of 60 times 0.3 times 0.7. That comes out to 3.55. All right, there's all our prep work. Let's go back up to the original question, which was, what was the probability of getting 10 or fewer heads? Now, don't forget here, this is your third criteria for doing the application of the normal approximation to the binomial distribution. We have to do a continuity correction. So the continuity correction is, and if you want to draw a sketch of it, you can think of it. We want to be at 10 and fewer. So we're looking at an area under the curve like this. We know our mean's around 18, so again, not to scale, but it gives you a perspective of where we are. And we want the 10 to be included. So if I blow that up, are we going to start at 10.5 or are we going to start at 9.5? Well, since we're heading to the left for area and we want 10 to be included, we're going to have to start at 10.5. So our correction looks like this. Okay. So in punching this into Google Sheets, we can, because it's an area of the curve from an x value and to the left, do it quite simply like this. Equals norm dist. Let's use our x value of 10.5 from the continuity correction. Let's use our mean of 18, our standard deviation of 3.55, and end with the word true, close bracket. When you hit enter, after punching that into a cell of Google Sheets, you should end up with a value of 0.0173, which you can convert to a percent if you like. You can make it 1.7%. Okay, I'm going to leave it as a decimal. Part 2 of this question says, what would the probability of getting, or be, of getting exactly 20 heads? Now we have to remember that the normal distribution is about finding areas under the curve. And if I have just a single line like this, I can't find the area of that. It has to have some width. So based on the continuity correction principles we learned in the last lesson, we're going to have to find the area under the curve then for half a unit before 20 and half a unit after 20, using that as inner and outer thresholds, if you will, finding the area of all of this. So our continuity correction would be from 19.5 to 20.5. So to find the area of this little wedge, if you will, we'll have to find the area under the curve from 20.5 on and to the left, subtract from that the area of the curve from 19.5 to the left, and then we'll be left with that little slice. So putting it into Google Sheets, we would do equals norm dist, and we will put in our higher value first, 20.5, same mean and standard deviation, and we subtract the area of the curve from 19.5 and less. That all goes into the same Google Sheets cell. When you hit enter in Google Sheets, you should end up with 0.957, which again, you can round to a percent if you like, 9.6%, or you can just leave it like this. Let's do one more example together. In this example, it states that 43% of Canadians will say that they don't like NHL hockey. You can decide if you want to believe that or not. Let's say you survey 1,000 Canadians. What's the probability that more than 400 of them will say, I don't like NHL hockey? Well, let's set up our parameters based on that information. So our number of trials is our number of people surveyed, which would be 1,000. The thing that we are trying to find is the number that don't like hockey. So let's make that quote our success. So the percentage that don't like hockey is 43%, so I'll write it as a decimal this way, which means the percent that do would be 0.57. And I want to know the probability of getting more than 400 people in that survey who would say they do not like hockey. So not including 400 has to be greater than 400. Let's also do some of the other steps we did in the other examples. We need to find the mean. It's n times p. You can see there's a lot of trials here, and the more trials there are, the better for applying normal approximation to binomial. 1,000 times 0.43 is going to give me 430, which is way bigger than 5, so I've met that criteria quite nicely. Maybe in your head you can do the NQ one, but if we're going to show our work, we probably should model it here too. 1,000 times 0.57 is going to be 570. That definitely is bigger than 5 as well. So we're good to keep going. Our next step is to find the standard deviation. It is the square root of NPQ. So, square root of 1,000 times 0.43 times 0.57. I'll save you some time. Make sure you can do it though. 15.66. All right, so let's answer this question. What is the probability of surveying those 1,000 Canadians if 43% of them say they don't like hockey? That more than 400 will say this. Don't forget, we've got to do a continuity correction. Okay. So if we're looking at, again, sort of sketching the curve to get an idea of what that continuity correction looks like, our mean is at 430, and we're at 400. This is definitely not to scale, okay, because the standard deviation is 15. This would be 2 deviations away because it's not too bad. And I want the area of the curve greater than 400, so I'm looking at this. Do I want the number 400 to be included? The answer is no. It says greater than 400. If it said greater than or equal to, I would want it to. So since I'm going this direction, finding the area, I'm going to do a correction to 400.5. So my correction will be the probability of x greater than 400.5. So because it's a greater than area, we have to do 1 minus the little white area. So equals 1 minus norm dist. Let's use 400.5. Our mean is 430. Our standard deviation is 15.66, and we end with the word true. That all goes into a cell in Google Sheets. And when you hit enter, you should end up with 0.97, which would be 97% chance of getting more than 400 people saying they don't like NHL hockey. Well, there you go. Have some fun with the practice, and as always, let me know if you have any questions.